Okay, welcome everyone. It's my big pleasure to introduce Eunjeong Lee from Pohang Institute of Basic Science, and this is part, I think, of University of Postech University in Pohang in Korea. And Eunjeong will speak about smooth toric Richardson varieties.
Okay, thank you very much for the introduction, and thank you for coming. This is my great pleasure to give a talk at the Zoom Algebraic Geometry Seminar. My talk is based on joint work with Professor Miki Yamashita in Osaka City University and Sun Jung Park. Today, I'm gonna consider about the smooth toric Richardson varieties. Yes, this is a plan of this talk. So I will first briefly explain what are Schubert varieties and Richardson varieties, which are quite interesting subvarieties of the flag varieties. So I will first explain the flag varieties and permutohedra, which is a polytope related to this flag variety, and then introduce certain polytopes, which are broad interval polytopes, which is related with these Richardson varieties. And then I will introduce a certain family of Richardson varieties called toric Richardson varieties of Catalan type. And then finally, I will provide how to enumerate isomorphism classes of these toric Richardson varieties of Catalan type. Okay, let me start. So what is a flag? Actually, the name of the flag variety coming from this figure, flag. Flag is really a flag. And we call a flag in Cn is a sequence of vector spaces. So V dot means that this is a sequence of vector spaces V1, V2, Vn minus 1, such that each of these vector space Vi is of complex dimension I. So actually, as you can see here, I have a flag and the origin sit inside this the root of the flag, and then this pore containing the origin, this corresponds to this one-dimensional vector space, and the two-dimensional vector space should contain this one-dimensional vector space like this. And if you collect all these flag in Cn, then it becomes a projective variety, and we call it the flag variety, FLCN. And it is well known that flag variety can be represented by a homogeneous space. Here, GL and C is the set of the this is the general linear group, and which is the set of n by n matrices such that the determinant is non-zero. And here, B is a Borel subgroup of GL and C. Since this GLN acts on this set of flags, if you consider, and this action is transitive, and if you consider the stabilizer of a certain flag, then you got a Borel subgroup B. And this is a smooth projective variety of, okay. I don't know why it is closed, but
Let's try again.
Try again. I'm sorry.
No worries, no problem. Yeah.
Yeah, maybe. Let me try again. Okay.
If there's a problem, one option, you can actually log out and then log in.
I see.
Oh no, it looks okay. It's fine. It's fine. Yes.
I wanna go to. Okay, this is the. I think maybe I was where. Yes, here. Yes. Yeah, flag variety is a smooth projective variety of complex dimension n times n minus 1 mod B, and the set of diagonal matrices, which is the complex torus of dimension n, act on the flag variety. So because this is contained in the Boer subgroup, and this T acts on GLN by left multiplication, and this induces an action of torus on the flag variety. And you can check that the set of torus fixed point is one-to-one correspondent to this symmetric group. So for a given permutation W, here I use the one-line notation of an element of the symmetric group. And for each element W, I will associate a coordinate flag WB, which is defined as follows. So the first vector space is spanned by this W1 standard basis vector, and my second vector space is spanned by these two coordinate vectors EW1 and EW2 and etc. So, and this we call it the coordinate flag, and this is a torus fixed point of the flag variety. And using the Plucker embedding of the flag variety, you can pull back the Fubini form in the project space, and by considering a moment map, you can see that this fixed point WB, the image of this fixed point WB is given by the inverse of each coordinate. So this is a certain point inside of this Euclidean space Rm, and the first coordinate is W inverse of 1, and the second coordinate is W inverse of 2, etc. And because of the convexity theorem, we can see that the moment map image of the flag variety is given by the convex hull of all of these coordinates or all of these points, and we call it this polytope the permutohedron. And because each of these points W lies on a hyperplane, lies on this hyperplane, this lives in certain n-1 dimensions of space, and indeed this becomes a polytope of dimension n-1. And as you may expect, there is a bijective correspondence between the set of vertices of this permutohedron and the symmetric group. And moreover, this polytope is simple. Here, a polytope is simple by mean that at each vertex, there are exactly n-1 edges emanating from each vertex. And moreover, the combinatorics of this polytope is well studied. So for example, the phase structure of the polytope and the H polynomials, which becomes the Eulerian polynomial, and the volume of polytope, and so on. And this polytope appears in the paper of Galfand and Seraganova in 1987. In this context, they studied the torus orbit in the flag variety. And in fact, they consider the closure of torus orbit, and there are several different toric varieties appearing in this way, and the toric variety given by this permutohedron can be expressed as the closure of certain torus orbit inside of the flag variety. Here I draw some examples of permutohedron. This on the left-hand side, this polytope having 6 vertices is the two-dimensional permutohedron related by S3. And here, this is the three-dimensional permutohedron. In fact, this lies in, it lies in four-dimensional Euclidean space, but I draw it in a three-dimensional way. And I want to mention that here I just put a certain permutation, but this permutation notation mean that this is a certain coordinate in the Euclidean space. And to define Schubert varieties and the Richardson variety, I have to, we need some, I have to introduce the broad order on the symmetric group, which is a partial order. So for a set of integers, say 4, 1, 5, 2, we define this notation, up arrow notation, by rearranging these numbers in ascending order. So this is this upward arrow gives a certain ordered d-tuple of number, ordered 4 tuple of numbers. And we put a lexicographic order on the set of k-tuple numbers in this way. So a1 da 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 ak is less than or equal to another sequence of numbers b1 da 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 bk if and only if each ai is less than or equal to bi for all I. And using this notation, we can define the broad order on the symmetric group as follows. So for two permutations v and w, v is less than or equal to w if and only if for each k, this tuple given by the first k numbers is less than or equal to this k tuple given by the first k numbers of w. Here I prepare an example. So let's first consider these two permutations, 3, 1, 2, 4, and 3, 4, 2, 1. Then this 3, 1, 2, 4 is less than or equal to 3, 4, 2, 1. This is because if you consider the first numbers appearing in this permutation, then you can see that 3 is equal to 3. So this inequality satisfies. And then consider the first two numbers, that is 3 and 1. And by rearranging these numbers, you got the tuple 1, 3. And by considering the first two numbers in this permutation, you got 3, 4. And by this definition, by this considering this lexicographic order, you got that 1, 3 is less than or equal to 3, 4. And similarly, you can see that 1, 2, 3, which is given by the first three numbers of this permutation, is less than or equal to 3, 2, 3, 4. Accordingly, 3, 1, 2, 4 is less than or equal to 3, 4, 2, 1. But 1, 4, 3, 2 is not, you cannot compare these two permutations. That is because 1 is less than 3, but 1, 4 is not less than 1, 3. And using this broad order on the symmetric group, the broad interval is defined as follows. So for two permutations, we use this interval notation by considering all the setup, by collecting all the permutations satisfying this condition, and we call it a broad interval. And for this broad interval is closely related to the Schubert variety and Richardson variety. The Schubert variety is a certain subvariety of the flag variety given by the closure of a B orbit of this fixed point WB. And the Richardson variety is the intersection of the Schubert variety and certain translation of another Schubert variety, and we call it an opposite Schubert variety. Here, W naught is the longest element in the symmetric group. And in fact, the family of Richardson variety contain all Schubert varieties, and also a Schubert, if you consider this longest element, the Schubert variety becomes the full flag variety itself. And the Richardson variety is not necessarily smooth projective variety of complex dimension LW minus LV. So this variety, the dimension of this variety is determined by these two permutations. And here the L of W is the number of inversions of the permutation W. And moreover, this torus which acts on the flag variety, this action induces an action of this Richardson variety. And moreover, if you consider the set of torus fixed point, then there is a bijective correspondence between this set and the broad interval, which collect all the permutations in between V and W. And we define a broad interval polytope by considering a convex hull of the point in Euclidean space such that Z is greater than or equal to V and less than or equal to W. And as you may expect, if you restrict your moment map defined on the flag variety on this Richardson variety, then the image becomes this broad interval polytope. Let me show you some examples of the broad interval polytope. Here on the left-hand side, I will show you this broad interval polytope given by two permutations 1, 2, 4, 3, and 2, 4, 3, 1. Here the start vertices are these two permutations. And here these red dots, there are 6 more elements, 6 more permutations in between 1, 2, 4, 3 and 2, 4, 3, 1. And then taking the convex hull, we got this 3-dimensional polytope, which is combinatorially equivalent to a cube. And I prepare one more example that is given by 1, 3, 2, 4 and 3, 4, 1, 2. Here I put the stars on the corresponding vertices, and there are 6 more vertices, 6 more elements in the symmetric group in between these two permutations. And by taking the convex hull, I got this 3-dimensional polytope. And if you consider the length, the difference of the length, then the difference of these two, difference of the length of these two permutations is the same as the dimension of my polytope. And on the right-hand side, I got also this equality. So I can say that the dimension of my Richardson variety is the same as the real dimension of the broad interval polytope. Actually, this polytope was studied in Zickerman and Williams' paper, and they studied combinatorics of broad interval polytopes, but there is still much to investigate. For instance, it is unknown when my polytope is simple. So for example, on the left-hand side, you may check that at each vertex, there are exactly 3 emanating vectors. So this polytope becomes a simple polytope. But for this broad interval polytope, you can see that at this star-shaped vertex, there are 4 edges emanating from this vertex, even while this polytope is 3-dimensional. So this is not a simple polytope. And here I want to provide our conjecture. Actually, we have conjectured that a broad interval polytope is simple if and only if the vertices V and W are both simple vertex in this polytope. Actually, these two examples provide a certain toric Richardson varieties. So because the dimension of this polytope is the same as the complex dimension of my Richardson variety, I can say that the corresponding Richardson variety is a toric variety with respect to this maximal torus action. And there are several studies on the on toric Schubert varieties. So using this, combining the result of Fan and Karpuchami and Grossberg-Karshun and so on, we can say that my Schubert variety is toric if and only if Schubert variety is smooth and toric. And moreover, this permutation W is a product of distinct simple reflections. Here, because my symmetric group is generated by certain simple reflections, so I can write down my permutation using these simple reflections. And in any expression of this, in any reduced decomposition expression of my W, that is given by distinct simple reflections. And moreover, if my Schubert variety is toric, then the corresponding broad interval polytope is combinatorially equivalent a certain cube of dimension LW. Inspiring of this work, we have studied toric Richardson varieties. Actually, not every toric Richardson varieties are smooth. However, if it is smooth, then we can say the following. So my Richardson variety is smooth and toric if and only if this broad interval polytope is simple of dimension LW minus LV. And that is equivalent to the following. My broad interval polytope is combinatorially equivalent to a cube. In fact, any smooth toric variety over a cube is a bond manifold. Here, a bond manifold is the total space of an iterated CP1 bundle. So any smooth toric Richardson variety becomes a bond manifold. From this, I want to address the following question. So which Richardson varieties are smooth toric? That is, when the broad interval polytope is combinatorially equivalent to the cube. And also, which bond manifolds can appear as smooth toric Richardson varieties? And today, I wanna consider both questions. Okay, so before defining the certain family of smooth toric Richardson varieties, I wanna show you a motivating example. So as I mentioned before, smooth toric Richardson variety, the family of smooth toric Richardson variety is contained in the set of bond manifold, which are certain smooth projective toric variety, or which is a set of toric varieties over a cube. And today we will consider toric Richardson varieties of Catalan type. Here you may expect this Catalan, there would be a relation between these toric varieties and polygon triangulations. Here, on the left-hand side, I have a certain toric Richardson variety, and this becomes one example of Catalan type, and I will explain how to associate this polytope with a polygon triangulation. And because this And it is well known that the set of polygon triangulations is the same as there is a bijective correspondence between the set of binary trees. And we will consider the isomorphism classes of toric Richardson varieties of Catalan type, and it will turn out that there is a one-to-one correspondence between these isomorphism classes and unordered binary trees. Okay, let me consider this example. So this is one of the most important example of this talk. Here, this is a broad interval polytope given by two permutations 1, 2, 4, 3 and 2, 4, 3, 1. Here, the coordinate of a vertex, for example, 1, 4, 2, 3, is really the coordinate in R4. So this 1, 4, 2, 3 denote 1, 4, 2, 3 in my 4-dimensional space. And at the vertex, because this is a cube, there are 6 codimension 1 faces, and I will compute all the normal vectors of this codimension 1 face. So I will compute the normal fan of this polytope. And to compute the normal fan, so to compute the ray vectors, I will use these edge vectors. So at the vertex 1, 2, 4, 3, there are 3 edges emanating from this point. And you can see that the primitive edge vectors are given by E1 minus E2. That is this vector coming from the edge connecting 1, 2, 4, 3 and 2, 1, 4, 3. And E2 minus E3, that vector given by this edge connecting 1, 4, 2, 3. And finally, E2 minus E4, that vector is given by this edge connecting 1, 2, 4, 3 and 1, 3, 4, 2. And similarly, near the vertex 2, 4, 3, 1, 2, 4, 3, 1, I got these 3 vectors. And they are minus E1 plus E4, and minus E2 plus E3, and finally, minus E3 plus E4. Because my permutohedron lives in a certain hyperplane, all of these vectors are contained in this lattice M that is given by, that is in this lattice G4 with the relation such that x1 plus x2 plus x3 plus x4 equals to 0. And let me consider the dual lattice, that is N. And the dual vectors lie in the quotient lattice. And I want to pick this basis of my lattice. So pi 1 is E1 and pi 2 is E1 plus E2. And finally, pi 3 is E1 plus E2 plus E3. And I want to let pi 0 and pi 4 by the 0 vector. Then the dual vectors, that is the primitive normal vectors to faces, are given as follows. So if you consider these 3 vectors, and the dual vector of these 3 vectors becomes this V1, V2, and V3, and W1, W2, W3, these 3 vectors are given by considering the dual vectors of these 3 edge vectors. And using these 6 vectors, I will draw a certain triangulation of 5 gon. So here, I will label the vertices of my 5-gon by 0 to 4 in the counterclockwise order, and then draw these edges by considering these coordinate vectors. So here V1 is phi1 minus phi4, so I will draw this edge connecting 1 and 4 in my polygon, and V2 is pi2 minus pi3, so I will draw this edge, and finally V3 is pi3 minus pi4, so I will draw this edge. And then I will consider 3 more vectors given by W1, W2, W3, and because W1 is pi0 minus pi1, I will draw this blue edge, and W2 is pi1 minus pi2, so I will draw this blue edge, and finally W3 gives us this edge connecting 1 and 3. And moreover, I want to mention that the relation, so I want to add Vi plus Wi, then you can see the following. So V1 plus W1 is the 0 vector, and V2 plus W2 is the same as W3, and V3 plus W3 is the same as V1, and you can see this relation on this polygon triangulation. So for example, this relation, let me consider this relation first. So V1 plus W1 equals to 0, corresponding to this polygon, this triangle connecting 0, 1, and 4. And V2 plus W2 equals to W3, corresponding to this triangle connecting 1, 2, 3. And finally, V3 plus W3 equals to V1 is related to this triangle connecting 1, 3, 4. And this is a certain pattern on this on this pair of permutations. So here we took, actually in the previous example, we took 1, 2, 4, 3 and 2, 4, 3, 1, and you can see that W in V, it starts with 1. So V1 equals to 1, and W is given by putting this 1 on the first coordinate, on the first position, to the last position of the permutation. So in general, the above observation holds for any pair of permutations V and W, such that V1 is equal to 1, and W by another permutation is given by putting in one-line notation. I will consider the numbers from the second of the V, and then through Vn, and finally put V1. So using these simple reflections, I can say my permutation W equals to that this permutation can be represented by putting simple reflections S1 through Sn-1 on the right-hand side of V. Or I can take another pair in this way. So Vn is n, and W is given by putting Vn on the first coordinate, and then put the other numbers from V1, V2, Vn-1. That is given, this pair is given in this way. And we say that a toric Richardson variety is of Catalan type when V and W is of the above form. In fact, if you take this pair V and W, then this always gives a toric-Richardson variety, and we call such a toric-Richardson variety is of Catalan type. And the reason why we call them of Catalan type is the follows. So we prove that using the association, as I mentioned, as I introduced before, for a given toric-Richardson variety of Catalan type of dimension n, I will associate a certain amplitude two-gon triangulation, and this map is surjective. And yeah, this is the reason why we call such toric-Richardson varieties of Catalan type. Let me explain a little more about the Catalan numbers. Actually, Catalan numbers we denote by Cn, and there is a closed formula of this Catalan number, and these are the set of numbers satisfy the following recurrence relation. So Cn plus 1 is the sum of Ci times Ci minus 1, and we set C0 equals to 1. And here is the first few terms of these Catalan numbers. And there are more than 200 many objects can be counted by these Catalan numbers. And there is a book by Stanley considering such object. And I want to introduce two of them. So as you may know, the number of triangulations of n plus 2-gon by adding diagonals which do not intersect in their interiors is, and Catalan number count such triangulations. And also the number of binary trees with n vertices can be counted by Catalan numbers. Here a binary tree is a tree. It is a rooted tree having at most 2 children, and we call it each of them by left or right children. So here I draw this double circle on the root, and you may think that these first 2 trees are the same, but they are different as binary trees. So we distinguish left and right child. So here from the root vertex, I have 1 right child, and at this vertex, at this node, I have 1 more right child. But in this binary tree, from the root vertex, I have 1 right child, but after that, I have 1 left child, because we distinguish left and right children. So these 2 trees are different as binary trees. Similarly, I can go from the left first. So from the root vertex, I have 1 left child, and then have 1 right child. And for this binary tree, I have from the root vertex, I have 1 left child, and then 1 left child. And this is a binary tree having 2 children. One is left and the other is right. And in fact, you can easily see that by putting a node in the interior of this triangle, you got the binary tree. And using these binary trees, we will enumerate these isomorphism classes of toric-Richardson varieties of Catalan type. And to consider isomorphism classes, we have to look at the combinatorics or the perimeter relation of the fan. Let sigma be the fan of a toric-Richardson variety of Catalan type, because we already know that such a toric variety has the fan, which is the normal fan of certain cube, there are 2n many ray vectors, and we let vk wk from k from 1 to n be the set of ray generators. And since sigma is the normal fan of an n cube, its primitive collection is given by each element of this primitive collection is this pair vk and wk. So there are n primitive collection. And here we show that the primitive relation. So if you add these two vectors vk and wk, then because this fan is the fan is a complete fan, it should contain in certain relative interior of another cone, and it becomes, we prove that this sum is the zero vector or another ray vectors v or w. And because of this lemma, we can say that a toric Richardson variety of Catalan type is Fano. And here, using this triangulation and the corresponding binary tree, we can see this primitive relation in a more in easier way. So this is our favorite example. And as I mentioned before, we got these three relations, and this is exactly what we call the primitive relation of a toric variety. And from this relation, I will draw a binary tree as follows. So this is an answer, but the way to draw this binary tree is followed. Because v1 plus w1 is 0, I will put 1 in the root vertex. Yes, 1 in the root vertex. And then consider this relation. So v3 plus w3 becomes to v1. So I will put 3, the number 3, as a child of my root vertex 1, and this becomes the right child. I will put it on the right hand side because this sum is v of something. So 3 is the right child of my root vertex. And finally, I will consider this relation. So v2 plus w2 becomes w3. So the number 2 is a child of my node 3. And here v plus w becomes w something. This 2 is a left child of my vertex 3. And by ignoring these numbers, we got this binary tree. And indeed, you can see that this binary tree is exactly the same one coming from this triangulation. And we can say that this binary tree encodes full information of my primitive relation. And because in general, the primitive relation determines the isomorphism classes, we will use that fact. We will use this combinatorics of binary trees. And an unordered binary tree is a binary tree without ordering. So as I mentioned before, the left or right, the position of each child is very important when we consider the binary tree. but unordered binary tree is a tree by ignoring this ordering. So unordered binary tree is nothing but a rooted tree having at most 2 children. So as unordered binary tree, these 4 trees are the same because by ignoring all the orders, I have the same tree, but this tree is different because it has 2 children at the root vertex. And here is our result. So the isomorphism classes, there is a one-to-one correspondence between the isomorphism classes of n-dimensional toric Richardson varieties of Catalan type and the isomorphism classes of unordered binary trees with n vertices. So it means that, as I mentioned before, there is a surjective map from the set of toric Richardson varieties of Catalan type to the set of triangulations. And because the set of triangulation is the same as the set of binary tree, there are 5 different toric Richardson varieties of Catalan type in this case. However, if we consider the isomorphism classes, then there are 2 different isomorphism classes of 3-dimensional toric Richardson varieties of Catalan type because there are 2 isomorphism classes of unordered binary tree with 3 vertices. And here is a way of proof. So we use the perimeter relation on this fan as follows. So let sigma and sigma prime be fans of toric Richardson varieties of Catalan type. If they are isomorphic, then there exists an isomorphism between the lattice and n prime. Here, n is a lattice corresponding to my sigma, and n prime is the lattice corresponding to sigma prime, and there is an isomorphism between these 2 lattices such that the ray vector Vk, the image of this ray vector is either Vk prime or Wk prime. So by reordering the ray vectors, we may assume that the image of Vk is either Vk prime or Wk prime. And we will consider how this makes the corresponding binary trees in a different way. So let Fk be the isomorphism of the lattice n, which interchanges Vk and Wk, but remains all the other ray vectors Vi and Wi. Then we can see that because the perimeter relation will be changed at around these vectors Vk or Wk, so the binary tree associated with the fan Fk of sigma is obtained from the binary tree associated with sigma, the original fan, by interchanging the left and right children of the vertex k. So by interchanging the left or right child does not affect on the isomorphism class. So this proves that this isomorphism class corresponds to the unordered binary tree with n vertices. Yeah, this is a way of proving this theorem. In fact, this number is a well-known number called Wedderburn-Etherington number, and the number of isomorphism classes of unordered binary tree with n vertices is known to be this number. And here I put a table considering some the first few terms of this Catalan number and Wedderburn Etherington number, Pn+1. And this number, the sequence of these numbers satisfy certain recurrence relation. So you can compute a little more terms. And actually Bn count several different objects, and our result add one new object, while Cn count more than 200 different objects. Okay, let me explain the future direction of my work, our work. Actually, this is a parallel figure that I show you at the beginning of the second chapter. So actually, among the full smooth toric Richardson varieties, we just consider certain toric Richardson varieties of Catalan type. So, and it is revealed that this family becomes a proper subset of smooth toric Richardson variety. So we have to add a little more toric variety to get the equality, and there are the candidate toric Schubert varieties. Because the all smooth toric Richardson varieties, the corresponding broad interval polytope becomes a cube, we may ask the following problem: find all pairs V and W such that the corresponding broad interval polytope is a cube. And our toric Richardson varieties of Catalan type provide a partial answer of this question. There are many pairs such that this polytope is a cube. For example, toric Schubert varieties are all smooth, and as I mentioned before, they provide a cubic broad interval polytope. However, one can check that not every toric Schubert variety is final. So we can see that this set of toric variety is not contained in Catalan type, toric Richardson variety of Catalan type. And one may ask that by considering this union, we got this inclusion or the equality. So we still don't know whether this inclusion is either the equality or the proper, or this union provide a proper subset. And we just consider certain extreme cases for these pairs W and V. And also I want to mention that we prepare that we have been studying the isomorphism classes of toric Schubert varieties. As I mentioned before, because these toric Schubert varieties are always smooth and we know how to describe its fan explicitly, we may check whether a given toric Schubert variety is final or not in a combinatorial way. And also by considering the primitive relation, we study the isomorphism classes of these toric Schubert varieties. And we studied their cohomology rings and so on. Okay, so these are the references of my talk. And okay, let me stop here. Thank you for your attention.
Thank you very much. Let's thanks Eunjeong in the Zoom. Just give me 1 second. Okay, good. Thank you very much for excellent talk. And okay, before I ask people for questions, I have some small questions. So you mentioned that these varieties are not fana, or not always fun. Yeah?
Yes.
But are they always like fana type? it means that there exists some boundary such that they log fana.
I'm sorry, could you, they are weak funnel.
Weak
toric
fana,
yes.
or maybe sometimes there's a notion called fana type. So it means there exists a boundary such that it's a log fana variety.
Maybe,
For example, in this case, they would be Mori dream spaces.
Mori dream spaces.
It's
Actually, I'm not familiar with that.
It's like a fana, but with a boundary.
Funnel.
With a boundary. So you have a boundary delta such that it's a log fana variety. Okay. So if just okay. Okay, there's a question. Yes, Yan Chen, please ask. Yeah.
Hi. Can you hear me?
Yes.
Okay. So my understanding is that you use the moment map to study the flag variety.
Yes.
And the toric Richardson variety of a Catalan type is special because their dimension because this moment map is almost like some kind of at least birational, like their dimension matches, right?
Yes, you're right. The dimension should match. Yes.
Right. And so my question is like how much information can we get from their moment polytope of a flag variety? I mean, since their dimension, in general, their dimension is not the same. So can we, how much information, for example, their cohomology of a flag variety can I read from their moment polytope?
Thank you for asking the question. So I think maybe I can answer the first part of the question. So actually the moment map, if I consider the restriction, let me move on maybe over there. So if I consider the restriction of the Richardson variety, then the moment map becomes this broad interval polytope. When this is toric, then the corresponding, so actually, because this is a projective toric variety, there is a corresponding certain polytope, lattice polytope.
Right.
And that should be this broad interval polytope. They are the same.
I mean, in this case, we know that we can use the combinatorics of toric variety to get a lot of information of this Richard variety. But how about the How about the other cases? I mean, when their dimension doesn't match.
That's a very good question, I think. But at this moment, I don't know much about it. But actually, I can say that as the Galfan-Saraganova, this permutohedron itself is one typical example, and they study certain toric varieties inside of the flag variety, and I can say that each broad interval polytope, even though the dimension doesn't matches, there exists a certain toric variety inside of the flag variety, which can be expressed as this torus orbit closure, and the corresponding polytope is the broad interval polytope.
Okay, I see. Okay, thank you.
Thank you.
Thank you, Eunjeong. Any other questions to Eunjeong? Okay, if there are no questions, let's thank Eunjeong again. Thank you very much.
Thank you very much.
Thank you. Have a good day, and see you at some point in real life in Pahang.
Hope to see you.
See you. Bye.
Thank
Bye,
you
everyone.
very much.
Bye.
Yeah, I will stop sharing.